Workshop 3. Measuring the colorant strength of dyes in fabric and garments. It is time to discuss measuring the colorant strength of dyes, a topic that's critical but often underutilized in the dyeing industry. Understanding how strong a dye is can make a huge difference in maintaining consistent color quality, adjusting formulations with precision, and ensuring smooth collaboration with suppliers. Today, we'll explore two key methods that help color professionals quantify dye strength and improve color performance: the static method and the dynamic method. Static method, measuring transmittance. The static method is a proven technique for evaluating dye solutions in their original liquid form. This approach uses color spectrophotometry to measure how much light passes through the sample, revealing the dye's optical density and concentration without requiring a specific starting formulation. How it works. 1. Standardize the instrument for transmission mode using the appropriate reference standard. 2. Prepare the dye solution in water and transfer it to a 10 mm optical glass cell. 3. Place the cell in a HunterLab transmission spectrophotometer, such as the Vista. 4. Measure the sample and compare the results to a known reference or standard. Key control factors, like solution temperature, complete dye dissolution, and fixed measurement timing, are essential to ensure data accuracy and repeatability. Why is this useful? Because even slight variations in dye concentration can change how the dye interacts with fabric. This method gives colorists a full spectral profile, far more informative than single-point absorbance measurements used in basic UV/VIS tools. Dynamic method, measuring reflectance. Now let's move to the dynamic method, which is more familiar in textile settings. This approach involves evaluating fabric samples that have been dyed using standard and incoming dye batches. Steps include: use directional color spectrophotometers like a Gira L2. Prepare lab dips with the same dye concentration, fabric weight, and dyeing time. Place each sample flat on the spectrophotometer port. Cover the sample with a white tile to ensure flatness and a consistent white background. Compare the reflectance curves of both samples under the same lighting conditions. This method provides real-world insights into how a dye behaves on fabric, capturing critical variables like dye penetration and pickup ratio. L-star values are especially telling. Lower L-star indicates darker shades, usually from higher dye concentrations. Science behind dye strength. Kubelka-Munk theory. To understand why these methods matter, we need to look at the Kubelka-Munk equation. It relates a dye's colorant strength to how it absorbs and scatters light. This gives rise to Ks values, which quantify dye performance. Imagine comparing two blue dyes. At first glance, they may look the same, but their spectral curves might show different shapes, indicating different absorption behaviors. Sample 2 might show a colorant strength of 76.9990% versus a standard. That's a meaningful difference, confirmed by lower Ks values like 1.4492 compared to 1.8821. This tells us sample 1, standard, will produce a deeper shade and likely require less dye in production. Scales and indices used. To evaluate color differences in dye strength, professionals use color scales, CIELAB, CIELCH, YXY. Indices, percent colorant strength, dominant wavelength, metamerism index, excitation purity. Differences: delta E star, delta H, delta C star, delta A star, delta B star, and delta metamerism index. Practical tips for better standardization. For consistent results: calibrate instruments regularly. Keep dye concentration, fabric weight, and time consistent. Apply proper dilution techniques for transmission measurements. Maintain consistent environmental conditions. Using both static and dynamic methods gives you a more complete picture of dye performance. The static method uncovers detailed spectral and chromaticity data, while the dynamic method shows how dyes behave on actual fabric under real conditions. Together, They provide a powerful toolkit for ensuring color consistency, improving process control, and reducing waste.